Hey, Dr. Clark coming back at you. Let's take a look at an example problem for doing statistical inference with matched pairs data. So our example problem is about baseball. So if you've ever been a baseball player, you'll know that when you're rounding first base, sometimes you don't go to first base and make a perfectly right corner. You kind of round it a little bit. And what we're investigating is whether you want to come way out wide and then slingshot through, or if you want to stay tight to the baseline the whole way around. Which of those base running strategies would give you the fastest time to second base, essentially? Of course, this could make, even milliseconds can matter here when you're playing baseball. So this is why they're, studying this. So this is coming from the 1970s. They looked at base running strategies. They took 22 runners and they marked them from a spot 35 feet past home to a spot 15 feet before second. So they wanted to focus in on the running portion. So not the sliding, not the starting, but just the running portion. So they're trying to pull out the variability there. And they had runners use both strategies. And so notice this is setting up a paired situation because the same runner runs both routes with a rest in between so that they're not more tired. And the other thing they did was they flipped a coin to see whether they would run the narrow path or the wide path. And that way some runners ran the narrow path first, some runners ran the wide path first. So hopefully any variation in choosing which one they ran first got averaged out between the two groups. So that's another sort of thing. And the paired design is controlling for runner-to-runner variability. So if they just split their team into two groups and had half of them run one route and half of them run another route, well, maybe all the fast people got in one group and all the slow people got in one group. And so the difference you observed wasn't connected to the route, it was connected to who got into which group. So this is the key to the paired design, is that the same runners run it both ways. And it was a randomized experiment because of the coin flipping. So this is the data. And what you'll see is very little difference between one runner to himself. Right? So, a particular runner might be very different from another runner, but not very different from themselves, right? And so the data has a lot of spread. You've got some slower runners and some faster runners and some middle runners. And when I look at this, I would say, okay, well, give me the averages. Okay, sure. The narrow route took a little bit longer than the wide route, but not much longer. And so I'm not sure that little bit of difference in the narrow route is statistically significant. But I do want to at least check it in the two means applet. So if you go to down here, first base, they've got the data right here. And if you go to multiple means, we can paste the data in, and you can see the box plots here and the data, and you can see it's only 0.07 seconds difference between the narrow group and the wide group. And so if we do a simulation here and we randomly deal the times into two piles and average them out, you get, let's see, what was our average, or 0.075. So if we plug in 0.075 here, yeah, I mean, it's not right on zero, but it's certainly not way in the tail. So our p-value is 0.3. So yeah, we did observe a difference, but that difference wasn't big enough for me to conclude that the narrow route is definitely faster or slower than the wide route, right? It just wasn't statistically significant. All right, so now let's see what happens when you look at the pairedness of the data. So here is all the runners on the narrow route, all the runners on the wide route, and what you see is most of the time they get faster, 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 faster. Now this guy got slower, that guy got slower, that guy got slower, and that guy got slower. So there was five runners that got slower on the wide route, but everyone else got faster on the wide route. Okay? So when I look at the differences, most of them are over here. And so I'm noticing a pattern. All of this variation that was happening between the different runners has now been condensed down, and we can see that the wide route is actually faster. Okay, so if we take all of these differences and average them up, that's our x bar, the average of the differences. It's still 0.075, but that standard deviation of the differences went way down. So the variation shrunk. And when you shrink the standard deviation, you're going to have much stronger strength of evidence. Okay, so let's set up the hypothesis test. Is the average difference of 0.075 significantly different from 0? So mu d, mu d is your average of the differences. We'll assume that's 0 for the null hypothesis, which is to say that in the long run it doesn't matter which route you take. On average, the two paths, the difference in times on average is 0. Or on average, the difference is not 0. On average, there is going to be a difference in time between the two paths. Okay? And we got that statistic, 0.075. It's definitely above 0, but is it far enough above 0 to be statistically significant? Okay? So how could we do this with a simulation? Well, the null says that running path doesn't matter. So what we're going to do is use the same data, and we'll just flip the differences according to a coin. Because if running path doesn't matter, then we should see what could happen by random chance if you just randomly allocated the two times to the two paths. And that will give us a null distribution, right? And then if we repeat that process many times, that will build up the null distribution. Okay, so let's go back to right here, the matched pairs applet. And if we paste in the data, here's the data, paste it in right here. Here's the same data here, and there's our differences that we saw, right? And we can see a lot of them are positive. So what the simulation is going to do is it's going to flip these coins, and whenever they get heads, they're going to switch the two times. And if they get tails, then they'll just leave them, okay? And when you do that, you'll get the differences. Sometimes will be positive, sometimes will be negative. And then we can see 0.075 whether what we observed in our sample is typical if you had sort of randomly allocated the paths to the two times, or not typical. And what you see is it's totally not typical. It's way out in the extreme. The p-value is 0 here. So remember, when we treated it as two independent groups, we got a p-value of 0.3. We did not get strong evidence. But when we use the matchedness of the data, the paired data, the p-value is now 0. We got very, very strong evidence. And that's because of this standard deviation. All of this spread got condensed down. Look, the spread went from 4.9 to 6.3. Now the spread went from 0.1 to 0.2. So it shrunk the spread down, which tightened up our standard deviation, which gave us much stronger evidence. Okay, and so, and we could do a 95% confidence interval as well. I think there's if they have a button here. Maybe they don't have a button here. So I guess I went ahead and computed the 95% confidence interval by doing what? Well, I know what, if I do this here, I get the standard deviation of the null distribution is 0.024, and so I can use that 0.024 as the standard deviation of the null distribution, multiply by 2, add and subtract it to my x bar of the differences, and make a confidence interval. And so what you can see here is that if you use the wide route, it's between 0.027 and 0.124 seconds faster than the narrow route. So we're 95% confident that on average, the narrow angle route takes 0.027 to 0.124 seconds longer than the wide angle route for runners like those in the sample. Now, of course, they're saying this because these are all professional baseball players in the sample. So this may not be true for just regular people, but that's what. So they put that little line in there. Okay. And then the exploration you're going to take a look at is jumping jacks versus bicycle kicks and heart rate, and the data's right there. So you want to use that when you do this. Okay. And of course, if you ever have any questions, just send me an email. Happy to go over the problems with you and spend more time explaining it. All right. We'll see you then.